Okay, starting with line plot. This is still Unit 6. So for this one, what we're going to do is create a number line, and then we make a dot or an X for each data point. And the good thing about this is it shows the individual scores. You also get to see the shape of the data. All right, so we're going to do this for number 2, which is, again, the test scores. So I'm going to start off with a number line. And our scores, the range of our scores went from 84 to 96. So I'm going to say 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98. All right, so that gives us an idea of what we're working with here. All right, so now what's going to happen is that I am going to go through and mark each test score so that every score is represented on here. So one of the scores was an 84, so I'm just going to use an X. There was an 85. There was an 88. We have a 93, a 94, and a 96. So this one wasn't very exciting because we didn't have any duplicates, but normally if we did, the X's would just go up above. So you can see that each score was only gotten or achieved one time. So that's what a dot plot looks like. All right, next up we're going to look at outliers. And what's different about outliers this year is that there's actually a mathematical definition to an outlier, and it is that it is 1.5 times the IQR, so the length of the box, basically. It's 150% of the box, which is where the 1.5 comes from. So for this one, we are going to use number 1, and I'm actually going to go look at number 5, because all of this is related. So on number 5, we did a box plot, and I like to use the box plot when I do the outliers, and I'll show you why in just a second. So what we're going to do from the data up here that we did with number 1, we know that our inner quartile range is 19. All right, so the inner quartile range is 19. And that, again, is the upper quartile minus the lower quartile. So now what we're going to do is we're going to take that 19 and we want to multiply that by 1.5. And that's where the 150% comes in. So if we multiply that by 1.5, that would be 9.5, so 28.5. All right, so 28.5 is our magic number. So now what I'm going to do is I'm going to go over to where the box plot was. So this upper quartile right here was at 58. So I'm just going to write that right up there. And then this lower quartile was at 39. All right, so what I'm going to do is I'm going to take this upper quartile and add the 28.5 to it. So basically what I'm going to do is extend that box a little bit. And this is something I kind of made up. It's not anything that's official. But I'm going to extend this 28. So if we add 28.5, it's going to be 86.5. So I'm going to extend this out to 86.5. All right, so that makes 86.5 the top boundary. So all I did was I took this and I stretched it out. So I added 28.5 to it. Well, what I'm going to do on the opposite end is basically the opposite. I'm going to take this 39 and I'm going to stretch it 28.5 this way. So if I do that, if I stretch this out 28.5 this way, then this down here is going to be 10.5. So now that's how I'm going to decide if I have any outliers. So when I look at this, I can see that I definitely have an outlier right here in the score that was 106. So when I go back to here, are there any outliers? The answer would be yes. 106 is an outlier. Now, if it asked, and this is what I asked on the quiz, if there isn't an outlier, I asked for the boundaries. So the boundaries would be 10.5 and 86.5. So if it was greater than 86.5, it's an outlier, and if it's less than 10.5, it's an outlier. So that's how I like to do outliers. All right, next up, this was just, we were looking at the shape and descriptions of data. So I just copied these over from the ones that we did our notes. We called this right here unimodal, and that was because there was one peak, where this one right here would be bimodal, because there are two peaks in the data. We also called this one symmetric, because we could definitely, if we split it right here down the middle, it's a reflection on both sides. And this one would be as 2. I don't even know what I'm saying. Anyways, I would call that one symmetric. This one over here, I would say, is bimodal, because we do have two peaks in the data. But I would say that this one right here is not symmetric, because if I cut this in half, it's not reflected. All right, this one right here, the purpose of this is to show that right here there is a gap. So we want to make sure that we don't skip numbers. We need to show all the numbers, and if there's something that's missing, that's okay. We can have a gap. This right here is going to show you what an outlier would look like. And what's important about an outlier is you won't have an outlier unless you also have a gap. So outliers wouldn't be outliers. They wouldn't be far away from the data if they had other ones in between here. Then these two are the ones that are skewed. This one is skewed on the right, and this one is skewed on the left. So that's the way I remembered it, was you went trick-or-treating and the families on the left side of the street didn't have any candy, but you scored really well on the right. So you were skewed left. All right, next up, two-way frequency tables. This is actually something carried over from Math 8. It kind of bleeds into the next thing with correlation, but what we do on here is you have categories. It's what we use to compare categories, and the goal is that in these columns here, we'll have the total numbers for these categories. So for example, there are 26 8th graders, and it looks like 20 9th graders. And then down across the bottom, we have the total of these categories. So we have 20 students taking dance, 16 in sports, and 10 that just go home and watch television. So our total 46 is because we have 46 students, and we get that this way and this way. Now we don't want to double that number, because then we're counting everybody twice. All right, so what we talked about was joint and marginal frequency. Joint boxes are the ones in here. So these are the joint boxes, and that's because they are joining the two categories. All right, these down here are our totals. These are the margins. That's the marginal frequency. And then when we do the conditional frequency, we're going to use both of them. So what is the marginal relative frequency of 8th graders? So that basically is asking how many 8th graders there are. So we want the margin over the total. So 26 out of 46. Then we'll grab a calculator. we'll do 26 divided by 46. We get a decimal, but we move it over 2 places, and I'm going to say 57%. All right, next one. What percentage of students are 9th graders that choose sports? Now, down here I wrote, look for the of. Okay, what percent of the students? So that's the total number of students. How many are 9th graders that choose sports? 9th graders that choose sports looks like 10. So we do 10 divided by 46, make that into a percent, and I got 22%. All right, of the dancers, so here we go. Of the dancers, so this is going to be a conditional frequency. Of the dancers, so what that tells me is that we don't even care about any of these people over here. Of the dancers, and there are 20 of them, what percent are 8th graders? Well, that's going to be 12 out of 20. So remember to look for the word of, because that's really going to help you figure out what your of the denominator should be. So we change that into a percent, and that's 60%. Next up, correlation. We talked about correlation and the correlation coefficient. We use the letter R. What it does is tells us how strong the relationship is between two categories. And it also tells us the direction with the positive and negative. And then causation is when one causes the other. Okay, so estimate a correlation coefficient. A person's weight versus the amount of exercise. Well, in general, the amount of exercise that you have does impact your weight. So I would think that the correlation coefficient for this would be pretty strong. All right, so I'm thinking I would estimate it as close to a 1. But let's think about it. As the person's weight increases, the amount of exercise they're doing probably decreases. So that would be a situation that would have a negative relationship. And then the more someone exercises, the less their weight would be. So as one goes up, the other one goes down. That causes a negative relationship. All right, estimate a correlation coefficient. Colors of the sky and the days of the week. I am thinking that should be somewhere around a 0. I don't really see any correlation between those two things. All right, number 12, is the above situation causation? So does exercise have an effect on a person's weight? I would say yes. All right, number 13, does the day of the week affect the color of the sky? And for that, I would say no. All right, I'm going to pause this video and pick up our graphing calculator right here at the end.